Good morning, students. In previous class, we have started with the D and F block elements, and we have seen clearly the difference between transition elements and D block elements also. And after completion of that introduction part, we have started with electronic configuration, general outermost electronic configuration of the D block elements. Okay, and yesterday we discussed that. In previous class, we discussed that this is the general electronic configuration of D block elements. N-1 D1 to 10, NS1 to 2. Why we got NS1 to 2 also I explained clearly. Because of some elements exceptional configuration, we are getting NS1 or 2. That's why we are giving commonly NS1 to 2. Generally, differentiating electron enters into D subshell from 1 to 10, N-1 D1 to 10, NS1 to 2. This is inner shell. This is inner shell and this is outermost shell. Just last but one. This is called penultimate shell. This is called ultimate. Ultimate is also called valence shell, valence shell, and this is penultimate shell. Okay. Now in today's class, we will continue that electronic configuration. The electronic configuration of zinc, cadmium and mercury are represented by the general formula N-1 D10 NS2. In this group, this is the last group of D block elements, zinc, cadmium, mercury. Its general configuration we can write it as N-1 D10 NS2. If you take zinc, zinc configuration is 3D10 4s2. Cadmium configuration is 4d10 5s2. Mercury configuration is 5d10 6s2. So on a whole, we are going to represent this general electronic configuration as N-1 D10 NS2 for only this group zinc, cadmium, mercury with completely filled D configuration. Okay, the orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. Transition elements should contain incompletely filled D subshells, whether in their common oxidation state or in their elementary form. But here, zinc, cadmium, mercury contains completely filled configuration in their common oxidation state or in their neutral form, that means elementary form. That's why these are not regarded as transition elements. Next, the d orbitals of the transition elements project to the periphery of an atom more than the other orbitals. The d orbitals of the transition elements project to the periphery means maximum it is related to. The meaning periphery we will get. Even the outermost configuration 4s it is there, this D block elements, even the outermost s orbital is there, but maximum characteristics depends upon this N-1 D configuration only for this D block elements. That's why mainly we will consider this along with this NS2 also, but mainly those characteristics depend on inner electrons also. That's why we included this one. Even though it is belonging to penultimate shell, we included this one as general outermost electronic configuration. Okay, now the d orbitals of the transition elements project to the periphery of an atom more than the other orbitals, S and P. Hence, they are more influenced by the surroundings as well as affecting the atoms or molecules surrounding them. In some respects, ions of a given Dn configuration n is equal to 1 to 9 have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristic properties such as display of a variety of oxidation states. These are all characteristics of transition elements which contains incompletely filled D configurations. Okay, variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. This one already we have seen, coordination compounds. Formation of complex formation. Complex compounds are also called coordination compounds with a variety of ligands. Okay, the transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. This is roughly they gave. These are all properties depending on electronic configuration. Like that they gave. Every property we are going to keep on side heading separately and we are going to discuss. Is it okay, ma? Formation of colored ions and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic property and magnetic behavior. All these characteristics have been discussed in detail later in this unit. Okay, there are greater horizontal similarities in the properties of the transition elements in contrast to the main group elements. However, some group similarities also exist. We shall first study the general characteristics and their trends in the horizontal rows, particularly 3D, and then consider some group similarities. So in this D block elements, we have similarities not only in the group. Generally in S and B block, generally we will see similarities in groups only, but here not only in the group, horizontal rows also maximum they will show similarities. Okay, so first we will consider general characteristics of these elements and we will go through side headings everything properly. Are you okay? Everything we will see the definition and after that how it is going to be discussed in this D block elements. First here we are discussing D block. Separately we will give F block later and we will discuss. Okay. Now let us see our next side heading. Our next concept. (8.3) that is general properties of the transition elements. Under this 8.3, first thing 8.3.1 physical properties. General properties of the transition elements, that is the main heading of 8.3. Under this different side headings we will see, that is 8.3.1 physical properties. Okay, let us start with this one. Nearly all the transition elements display typical metallic properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, strongerness, ductility. We can draw them into wires. The nature of the substance, if it is drawn into wires, that nature is called ductility. Malleability. These metals can be converted into sheets by hammering easily. High thermal and electrical conductivity. Thermal conductivity means good conductor towards heat. Electrical conductivity means good conductor towards electrical energy. And metallic luster. Luster means smooth and shining surface. Okay, ma? With the exceptions of zinc, cadmium, mercury and manganese, they have one or more typical metallic structures at normal temperatures. Normally, some exceptions will be there. Out of all these elements, definitely some exceptions might be raised. Is it okay, ma? Now, with the exceptions of zinc, cadmium, mercury and manganese, they have one or more typical metallic structures at normal temperatures. See, They have given a tabular column related to lattice structures of transition metals. This is for reference purpose only. No need to remember all these lattice structures. Just in term 1 solid state, we have seen that different types of lattice structures: CCP, HCP, FCC, like that. Okay, scandium will get HCP. BCC means body centered cubic. Titanium, HCP, BCC. Vanadium, BCC. Actually, this is HCP body centered. Hexagonal close packed, under that body centered. This is normal cubic body centered. Chromium body centered. Manganese HCP. Iron BCC. Cobalt CCP. CCP or FCC both are same only. Nickel CCP, like that. Zinc HCP. These are the lattice structures of various elements present in D block elements. This is for reference purpose only. Okay, see, BCC body centered cubic, HCP hexagonal close packed, cubic close packed, X atypical metallic structure. Wherever they have given X, that is the atypical metallic structure. Okay, ma'am. Our next thing is the transition metals, with the exception of zinc, cadmium and mercury, are very much hard and have low volatility. Low volatility is nothing but they cannot be converted to gaseous state easily. That is the meaning of low volatility. The transition metals, with the exception of zinc, cadmium, mercury, these are somewhat soft. You know that mercury is existed in the form of liquid state at room temperature. So these are not that much hard, these are soft, are very much hard and have low volatility. Low volatility is nothing but they cannot be converted to gaseous state easily. Their melting and boiling points are high. Because of very close packed with each other, their melting and boiling points will be high, as the structures are very hard. Figure 8.1 depicts the melting points of the 3D, 4D and 5D transition metals. Figure 8.1 depicts the melting points of the 3D, 4D and 5D transition metals. The high melting points of these metals are attributed to the involvement of greater number of valence electrons from n-1d in addition to the ns electrons in the interatomic metallic bonding. See, here the figure 8.1 was given. On x-axis we have taken atomic number. On y-axis we have taken melting point. On x-axis atomic number, on y-axis we have taken melting point. If you observe, titanium, vanadium, chromium, manganese again getting down melting point. From manganese to iron, again melting point is increased. Iron, cobalt, palladium, nickel, cobalt, nickel, copper. Same type of structure, same type of variation is observed in next series, 4D series. This is 3D series, red line. This one blue color, it is 4D series. Zirconium, niobium, molybdenum. Up to here melting point is increased, like up to chromium. See, same like that. After molybdenum, technetium. What happened to melting point? Decreased. Here also manganese, it is decreased. From technetium to ruthenium, again it is increased. Ruthenium to rhodium, like that it is observed for 4D series. But coming to 5D series, hafnium up to tungsten, it is increased. Up to tungsten it is increased. Again rhenium, osmium, iridium, platinum, again it is getting decreased. This is better understood by seeing the unpaired electrons. When number of unpaired electrons are increased generally, when number of unpaired electrons are increased, what will be happened? Melting and boiling, melting points will be increased. Why it is happened? General explanation I will say. Exception cases I will show it in the textbook and I will read. Now, first, how it is related, these metallic structures and melting points related to unpaired electrons. Let us consider titanium electronic configuration, argon 4s2 3d2, right? 3d contains 5 orbitals in which it contains 2 unpaired electrons. This 4s contains completely filled electrons only. These are not unpaired electrons, completely paired electrons. So on a total, on a whole, titanium has how many unpaired electrons? 2 unpaired electrons. Okay. Suppose this is one titanium atom which contains 2 unpaired electrons. This is another titanium atom which contains 2 unpaired electrons. How we are going to explain the bond between this titanium and titanium? That is nothing but metallic bond. This metallic bond is not like covalent bond or ionic bond. Now observe this first titanium atom contains 2 unpaired electrons. These 2 unpaired electrons spins in clockwise direction. Next titanium atom, 2 unpaired electrons. Those 2 unpaired electrons spin in anti-clockwise direction. Because of spinning of this electron in clockwise and this electron in clockwise, magnetic moment, that is nothing but magnetic field will be developed between the magnetic field will be developed around this electron and this electron also. Both are in same direction. So let us consider example as North Pole. This titanium contains 2 electrons, 2 north poles, addition only. This one, 2 south poles. Between North Pole and North Pole attraction, between North Pole and South Pole attraction, even between North Pole and South Pole attraction will be there. 2 attractions are present. These are behaving like 2 tiny magnets. This is one magnet and this is another magnet. Both contain same North Pole only. This is one magnet, this is another magnet. Like tiny magnets they are behaving because of spin. This one explanation already we have seen in previous sections also, previous classes also. When an electron, a charged particle, moves or spins around itself, it will be developed by magnetic field. According to physics also we have seen that one. If it is the reverse direction, means opposite direction. Suppose this electron spins in clockwise and this electron spins in anti-clockwise. Both have same magnitude but the directions are different. When the directions are different, automatically magnetic field direction also will be opposite only. So when this is North Pole and this is South Pole. So one tiny magnet with North Pole, one tiny magnet with South Pole. One tiny magnet with North Pole, one tiny magnet with South Pole. Between this attraction, 2 attractions are present, both are added, in which this titanium has strong metallic bond. This titanium has strong metallic bond when compared to scandium. Why? Scandium electronic configuration is argon 4s2 3d1. Scandium has only one unpaired electron. Titanium has 2 unpaired electrons. Scandium has only one unpaired electron. So if you see between 2 scandium atoms, that attraction will be developed by only one unpaired electron. Because of that, only one attraction between tiny magnets will be developed, and even this is also called metallic bond only, but this is because of only one electron, unpaired electron. Titanium has two unpaired electrons, the attraction will be strong. So when the attraction is increased, see scandium, titanium, vanadium. Scandium has one unpaired electron, titanium has two unpaired electrons, vanadium has three unpaired electrons. Like that, number of unpaired electrons are increased. When the number of unpaired electrons are increased, attraction increases. That means interatomic forces increase. Here that interatomic force is metallic bond. Interatomic forces are increased. When the interatomic forces are increased, they are closely packed with each other with very strong force. Because of that, melting points are increased. Even the metals are getting very hard. That is the thing we have seen till now. I hope you are all understanding the concept, ma. When the number of unpaired electrons are getting increased, the metallic bond strength also increases. When the metallic bond strength increases, automatically the attraction is increased. Because of that, the metal is getting hard and they have high melting and boiling points. Generally melting points we'll discuss here because they are all solids, na? Okay? Automatically their melting points will be increased. This is the main reason how these melting points are related to unpaired electrons. I hope you are clear. If you see vanadium, vanadium has three unpaired electrons. Three unpaired electrons are behaving like three tiny magnets. This is one attraction, 2, 3. Three attractions are getting very strong attraction. Three attractions are leading to very strong attraction. Chromium, 4 unpaired electrons. So between one chromium atom and another chromium atom, very strong attraction will be present when compared to vanadium also. Is it okay, ma? Even here, we will consider the 4s electrons also. Okay? Now let us see the explanation of this one. Even 4s has one unpaired electron means that unpaired electron of one chromium and another chromium. Actually, chromium electronic configuration is 4s1 3d5. This is unpaired electron only. Exceptional configuration, ma. 1, 2, 3, 4, 5. These are also unpaired electrons. I think this is the explanation we are going to give for chromium. Let us see how they have given. Okay. So final conclusion is, when the number of unpaired electrons are getting increased, metallic bond strength increases. I hope you are understanding, everyone. Because of opposite spins, this is developed by one tiny magnet north pole. This is developed by one tiny magnet south pole. Then there is attraction between this one and this one will be added when the number of unpaired electrons are increased. Like that, metallic bond strength increases. When the metallic bond strength is increased, automatically the metal is getting hard and melting point also increases. Okay, now the transition metals are very much hard and have low volatility. Their melting and boiling points are high. Figure 8.1 depicts the melting points of the 3D, 4D and 5D transitional metals. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electrons in the interatomic metallic bonding. See, interatomic metallic bonding. Here, the interatomic forces are nothing but interatomic metallic bonding. In any row, the melting points of these metals rise to a maximum at D5. Up to D5 they will increase. Again, if you see D6, D6 configuration contains 1, 2, 3, 4, 5, 6. 4 unpaired electrons only. D5 configuration contains 5 unpaired electrons. So from D5 to D6, again number of unpaired electrons are decreased. When number of unpaired electrons are decreased, again melting points will decrease. That's why up to middle, maximum up to middle, it is getting increased. Melting points are getting increased. Because left to right in a D series, number of unpaired electrons will be increased up to the middle and then again decreases. Number of unpaired electrons increases up to the middle and then again decreases. See now that explanation only. In any row, the melting points of these metals rise to a maximum at D5 except for anomalous values of manganese and technetium. See, these are important. Manganese and technetium, exceptions these are. Remaining all follows exactly. For example, if manganese is here, according to our regular trend, titanium, vanadium, chromium increased, manganese also increased, again iron decreases only, again slightly up to copper it is decreased. So increases and again decreases. But manganese is showing one exception, that it is containing less melting point than chromium. Again from manganese it is increased to iron. Here also same, technetium also. D5 except for anomalous values of manganese and technetium and fall regularly as the atomic number increases. They have high enthalpies of atomization, which are shown in figure 8.2. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly. We will see that explanation. Is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons. See the point here. In general, greater the number of valence electrons, stronger is the resultant bonding, that is called metallic bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization, that is very high boiling point, tend to be noble in their reactions. See later for electrode potentials. Actually these electrode potentials values, those were deleted for us. But here the conclusion of this point is, when the enthalpies of atomization is high, once see here, since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization tend to be noble. Noble means they won't undergo reaction. Okay, what is the meaning of this point? We will see the explanation. Before that one, we want to know enthalpy of atomization. What is meant by when enthalpy of atomization? Is it okay? Shall we see that one? Till now, I hope you are clear only what are the things they were explained. Now our next side again is nothing but our next definition. Enthalpy of atomization. This is one titanium atom, this is another titanium atom. Like that, titanium metal is present with closely packed with each other. Okay, in this titanium we have two unpaired electrons, in this titanium also two unpaired electrons. There is a certain attraction between titanium atoms. Here also we said there is a certain attraction between titanium atoms. Like that, they are very closely packed with each other. Because of how many unpaired electrons? Two unpaired electrons. Okay, now the thing is here, even between sometimes these two atoms also attraction will be there. This is like resonance. Remember, every time attraction will not be present between these two atoms only. Is it okay? Now, if you take this atom, after some time, attraction will be converted between these two atoms. At the time, this one will be bonding with this atom. At the time, this one will be bonding with this atom. Like that, it is like a resonance. When there is attraction here, it will be absent. Are you okay? Like that, they will be keep on exchanging the attraction. That's why every two atoms are getting attracted on a whole. On an average, every two atoms are getting attracted by the interatomic force, that is called metallic bonding. Is it okay? It is like resonance only. Suppose this metal atom is in a metallic bond with this metal atom for some time. Immediately this one will be bonded with this metal atom. Again it will be bonded with this atom. Like that exchange of these attractions will be taken place, leading to on a whole strong attraction between this one and this one also. That is called metallic bonding only. Okay. Now how this metallic bonding is related with enthalpy of atomization. Now the solid is present with very strong attraction or whatever it is, with a strong intermolecular interatomic forces. Now I want to convert this solid to liquid atoms or gaseous atoms. Not liquid atoms, but gaseous atoms only. Now I am going to convert this solid state to gaseous atoms. That means completely I am going to break this interatomic metallic bond. Completely I am going to break this metallic bond. For that, how much amount of energy is required? The amount of energy required to break the interatomic forces between the metal atoms to convert the solid state to atomic state. That is called enthalpy of atomization. Enthalpy is nothing but energy. Enthalpy is nothing but energy. The amount of energy required to convert this solid state metal to a atomic state metal is called enthalpy of atomization. Generally it will be calculated for 1 mole. So units of this enthalpy atomization is also kilojoules per mole or joules per mole or calories per mole also we can take. Okay, whatever it is, this is the definition of enthalpy of atomization. That interatomic force is there na, that metallic bond should be completely broken. Till that we have to supply some amount of energy. Okay, that amount of energy required to break that metallic bond, the amount of energy required to break that metallic bond and to convert that solid state metal to gaseous state atoms is called enthalpy of atomization. Is it okay, ma? Completely that metallic bond must be broken. For that, how much amount of energy is required? That energy is called enthalpy of atomization. Now, when the number of unpaired electrons are increased, that metallic bond strength also increases. Na? When the metallic bond strength is increased, it is required with high enthalpy of atomization. Correct? Automatically, energy of atomization is also high. When the attraction is increased between two atoms, we need more amount of energy to break the force. Here only 2 unpaired electrons are there. Suppose another atom is there which contains 3 unpaired electrons. There more amount of energy is required. The atom with 4 unpaired electrons, it is containing more enthalpy of atomization. Is it right? Correct only, na? So amount of energy required to break these forces, when number of unpaired electrons are increased, that energy also increases. That is about enthalpy of atomization. Now they have given one diagrammatic representation, that is graphical representation, to show the enthalpy of atomization's values. Okay, let us see that one. Before that, see this one. Another generalization that may be drawn from figure 8.2, this is figure 8.2, is that the metals of the second and third transition series have greater enthalpies of atomization than the corresponding elements of the first series. This is first series. These are first series elements. These are second series elements. And these are third series elements. First series elements contain low enthalpies of atomization when compared to second series. When atomic number is increased, also enthalpy of atomizations will be increased. Okay, number of electrons will be increased automatically. Number of electrons is nothing but, actually here number of shells are getting increased. From 3D to 4D, number of shells are increased. When the number of shells are increased, automatically attractions between the atoms also increased. according to that, melting points are also getting increased. So 3D series contain less enthalpies of atomization when compared to 4D series. 4D series contain less enthalpies of atomization when compared to 5D series. Let us see this one. Another generalization that may be drawn from figure 8.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition elements metals. Okay, observe here, on x-axis we have taken atomic number, on y-axis we have taken enthalpies of atomization H0 in terms of kilojoules per mole. What is the unit, ma? Kilojoules per mole. First increased up to here, chromium I think here. Again manganese has low enthalpy of atomization. That reason we will see later, ma. From chromium to manganese exception is there. This is manganese. This is technetium. Okay. Same in melting points curves, how they are like that here only. And one more thing. These graphs are very important. These graphs are very important, and we can expect this type of questions in our term 2 exam. So we have to be very careful about these graphs. So up to here chromium it is increased only. From chromium to manganese it is decreased enthalpy of atomization. Again it is getting increased and showing this like this curve. Is it okay, ma? These are the curves which shows variation of enthalpies of atomization with respect to atomic number. From this we can conclude one thing, that is, when number of unpaired electrons are increased, enthalpies of atomization are also increased. When enthalpies of atomization are also increased, automatically melting points are also getting increased, with the exception of manganese and technetium. That one we will see. Okay, ma? I will give explanation in the later classes. I hope till now what is the thing we have discussed, general physical properties. You are clear, I think. Any sort of doubts you can reach me by WhatsApp or through call also, no problem. Okay, I will help you and I will clarify your doubts, ma, anytime. And this is the explanation 8.3.1, that is physical properties. After this we will go through variation in atomic and ionic sizes of transition elements, transition metals we will see. Before that, everyone, you are understanding the concept clearly and follow the notes, which is very important for the revision. Okay, now coming to this 8.3.2, variation in atomic and ionic sizes of transition metals. Generally, left to right, what will be happened? Left to right, what will be happened in atomic size? Atomic size decreases. Is it correct? Top to bottom, what will be happened? Atomic size increases. Top to bottom, atomic size increases. Left to right, atomic size decreases. That one only, but one very important point is there, that is lanthanide contraction, which is related to F block elements, actually. That one deeply we have to study, because this is very important and we can expect a question from lanthanide contraction also. We will see clearly when we get that F block elements, and even here also they gave that explanation. That only here simply might be they have given the term only, lanthanide contraction, but majorly this lanthanide contraction will explain in F block elements, because this is related to F block only. Okay, let us see. In general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. Left to right, remember in periodic table, left to right, what will be happen to atomic size? It decreases only, na? That point only they gave here. See, in general, Ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. Electrons are coming into same subshell only, but nuclear power is getting increased by unity. It may be recalled that the shielding effect of a d electrons is not that much effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. Now the point, whatever the point I explained, I will explain. The same trend is observed in the atomic radii of given series. However, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. The curves in figure 8.3, next curve we will see that one, show an increase from the first to the second series of the elements, but the radii of the third series are virtually the same as those of the corresponding members of the second series. This phenomenon is associated with the intervention of the 4f orbitals, which must be filled before the 5d series of elements begin. The filling of 4f must be filled before 5d results in a regular decrease in atomic radii called lanthanide contraction, which essentially compensates for the expected reason. Now, what is this thing? On a whole, what is the explanation I am going to give now? Let us see how we are going to give the explanation. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are the elements present in first series. Okay, when we write the electronic configurations, argon same only, 4s2 3d1, 4s2 3d2, like that, 3d3 up to 3d10 we have. Is it okay? Now this is the nucleus of scandium, which contains 21 protons. First shell, second shell, coming to third shell and fourth shell. Here 4s2 electrons are present. This is 3d1. 21 protons. Here we have nuclear charge. Okay, electron comes into 3d1. We know already 3d screening effect order mask, shielding effect order, S is greater than P is greater than D is greater than F. In this we can tell D and F have very poor shielding effect. Electrons present in D and F subshells will create very less shielding effect when compared to S and P. Okay, so when the shielding effect is less here, this nucleus will attract the 4s electrons strongly. Shielding effect means it is not acting like a good screen. It is not going to reduce the attraction between nucleus and outermost electrons. That is nothing but screening effect. Like one shield, it is not going to happen because of very irregular shape. Very difficult to draw the shape for D and F. When the shape of the orbitals is getting complication in drawing the shape of orbitals is increased, shielding effect decreases. Okay, when the shape is getting difficult, shielding effect is reduced. D has greater shielding effect than F because F orbitals have very improper structure when compared to D shapes. Now coming to this point, when it has poor shielding effect, This nucleus can hold the 4s electrons strongly. Now coming to titanium, 22 protons are there. 3D contains 2 electrons, 4s2. 3D electrons are weak shielding effect. They will not cause that much shielding effect. Poor shielding effect they will show. Here also, but here 1 electron, here 2 electrons. They will not cause that much shielding effect. Then when they have poor shielding effect, but here nucleus has 22 protons, here nucleus has 21 protons. Nuclear charge is increased, poor shielding effect. Because of this, these 22 protons will hold the 4s electrons very strongly when compared to scandium. This is scandium, this is titanium. When compared to scandium, titanium nucleus will hold the 4s electrons strongly. Because of that, scandium size is, see, somewhat distance between nucleus and outermost shell. But titanium, the distance will be, but in titanium, the distance will be slightly reduced, because when the attraction is increased, this outermost shell will be coming closer to the nucleus. Because of that, distance between nucleus and outermost shell decreases. That is only atomic size. Next, scandium, titanium, vanadium. Vanadium contains 23 protons, 3d3, 4s2. Further shielding effect is less, but nuclear charge is furthermore increased. Then this nucleus will hold the 4s electron furthermore strongly. That's why when the shielding effect is reduced and number of charges, nuclear charge is increased, this nucleus will hold the outermost electrons very strongly. When the attraction between this nucleus and outermost electrons are increased, distance between the nucleus and outermost shell decreases, and atomic size decreases. Automatically ionic size also decreases. So this is already known to us, but here with the help of shielding effect also we are explaining. In left to right, generally atomic size decreases. This is general thing only, already we have seen also. In general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that much effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. Up to here, we will complete this one. And next point onwards also, it is very important. And in that, lanthanide contraction also will come. Okay, we will see that explanation in the next class. What is the importance of that lanthanide contraction, and it is compared with the 3D series, 4D series. Till now I am comparing with 3D series elements left to right only. Next, this point, to understand this point, we want to go through one series and another series, 3D and 4D comparison, 4D and 5D comparison. Means like a group wise we will see. Okay, ma? That one in the next class we will see. Now in this today's class, we have discussed that general electronic configuration continuation. Okay, and after that 8.3.1 physical properties we have seen. Under that physical properties, what about their melting points, enthalpies of atomization, all these things we have seen. And even we started with variation in atomic and ionic sizes also, till in a period like that we have seen. Next class we will start with what will be happening in atomic size and ionic size when we compare with group. Is it okay, ma? That is about today's class. I hope everyone is clear. If any sort of doubts, you can ask me. I will clarify your doubts. Thank you all. Have a nice day.